Swayam Prabha. Digital India. Educated India.
Hello and welcome to a new topic of discussion today. Today we are going to start with the topic of the stress-strain transformation. Now this topic essentially relates with the concept that if you are looking at a body, within a body, if you have a particular point, right, and within the same point, if you are looking at a different set of axes, at a different plane which is passing through the element, how do the stresses change? Now remember that for these particular cases we have mostly looked at sections or points within the body where we draw the section plane which is perpendicular to the longitudinal axis. And why did we do that? Because it's easy to do. We can easily derive the stresses and the strains and so on, right? But now what we are going to look at, that within the same point within the body, it's not a different body, we're from, and then the same point within the body, if we are looking at a different plane, then how do the stresses change? Now you can do this in many different ways. You can just go by the plane mechanics. You can take the section plane and you can resolve the forces, but you will see that there is a loss of generality over there, that for all the different planes that you take, you always have to go back and derive some of the equations of the stresses and the forces and so on. This particular chapter on stress-strain transformation essentially makes your life easy from the concepts you have already learned for sections which are perpendicular to the longitudinal axis. If you know the stresses, if you easily know the stresses in those sections, how do you find the stresses at any set of axes, at any plane which passes through the same point within the body? So let's go ahead and take a look. Now, as I was saying, that this is a concept, right, which you have been exposed to earlier for some special cases. Now let's take a look at some of the special cases which we have already seen. For example, if you remember that we had seen for the case of the pure axial load, remember when we have this P and P which is pulling, right? We have this P over A which is there, and for the same thing, for the same body which we have, if we take a plane which is along that 45-degree angle, this is one of the special cases. For example, for the material wood, we have seen, right, that the wood is particularly weak in shear, and the shear tends to peak up when your theta, that angle of rotation that you see over here, this theta becomes equals to 45 degrees. And for that, what we had seen, like, let me turn my pen on, what we had seen that the failure planes typically happen at these 45-degree angles that you see over there. So we have been exposed to some of these concepts as some special cases. Now remember, this is within the same point within the body, within the point A over here. As you see, if you take a a perpendicular section, whereas, and at the same point, if you take a 45-degree section which is shown for another point B over here, then you tend to get these kinds of stresses that you see over within the body. We have also seen this concept for the torsion. For the torsion, remember that if you take a small chunk of the element, a small element within the body which is inclined and perpendicular to the longitudinal axis, it is an element which is in pure shear. Whereas for the same body, remember our famous experiment, the chalk experiment that we did, there also we saw this these failure plane angles was happening at that 45 degrees. So these are the special cases. Now you might be wondering that now instead of 45 degree, if I take a 30-degree plane, if I take a 20-degree plane, that how are the stresses going to vary? So you can, again, as I said, you can derive these from the concepts of pure mechanics, but it just becomes very tedious. So this chapter focuses on making your life easy in providing you some easy set of relationships where you can just transform the stresses from the sections with a perpendicular to the longitudinal axis to any plane which passes at any particular angle. So this is the main objective of this chapter. So what it essentially looks at, if you have a body, this is a 3D small element that you have taken, infinitesimally small. So if you have these set of stresses which are acting within the body, if you are looking at a rotated element over there at the same point Q, so please observe this particular point Q that you see at the same point Q, if you are looking at a rotated element over there or a different plane of section, that how do the stresses and the strain get transformed when you're looking at this different plane. Now why is it important? Why do we need to study this? Well, a couple of reasons you already saw. That for the wood which is say weak in shear, the failure, even though if you are pulling or pushing with forces perpendicular to the normal plane, the failure may happen at an arbitrary angle than what you expect. And this is true for many of the structures that if you look at other kind of structures, you will see that in many of these structures, depending upon the loading, the failures may happen at very different planes. So ideally within a structure, you should be able to draw these, you see this one over here, these are the contours of the stresses. So these contours of the stresses are usually obtained by transforming within the same point. You transform the section, and you every time you plot the peak stresses which are happening at the different points within the body, essentially to track that how the body fails, along which plane is the body going to fail, right? So we are going to delve deeper into this one through the transformation of the stresses. Now within these ones, although I showed you the 3D diagram over here, particularly for us civil engineers and also mechanical engineers, it often suffices to look at 2D elements, and I will tell you why. For example, and 2D stress elements, remember we had discussed that these are the which are the elements. This is the plane stress element. That is, if you have a body over here, then in that particular case you have no stresses about the z axis. Remember, this was the plane stress case where you have the sigma z equals to 0, tau zx equals to 0, tau zy was equals to 0. And why is this relevant? Well, if you see for several of the elements that you see in our daily life, for example this spanner example which we have seen, and the most classic example, if you take a look at beams, if you take a look at the beams in your buildings and so on, these beams usually this vertical dimension and the length of the beam is usually quite high compared to this lateral, this transverse direction that you have over here. So if you take a small element within the beam that you see over here, this small element, and if you are say loading it with a load which is acting in that y plane over there, essentially the stresses in the z direction tend to vanish or tend to become 0. So within the beams also you have several of these plane stress elements which are acting over there. Now if we isolate these elements, as you can tell, this is sort of a representation of this one over here, where your sigma z, tau zx and tau zy becomes equals to 0. Now if you take this isolated element and if you just write it over here, so this constitutes a plane stress 2D element, and this is the crux of this chapter. We are essentially going to deal with the small elements over here, and as you see, this element that you have here, this particular face and this particular face are cut perpendicular to the longitudinal axis of the beam, and these faces over here are parallel to the longitudinal axis. So essentially either perpendicular or parallel over here. Now for these elements, we will see at the same point within the body, if you rotate the element, and I will show you the figure in a minute, if you rotate the element, how do these stresses change? What happens to sigma x? What happens to the tau xy over here? Now one very interesting thing you may note that among all these stresses, the one which is always easiest to draw is the tau. Why? Because once you draw one tau over here, all the other arrows that you see, these guys becomes automatically fixed. Why? Because if this points vertically up in the opposite face, to balance that one you must have a vertically down force, right? Now these two over here in this case will result in an anti-clockwise moment. So to balance that, you have to have a clockwise set of tau, so which is these guys over here. So if you have one tau, the other tau automatically. These are small interesting tidbits which will help you draw the stress element in the rotated plane that we have over here. Now before we go ahead, let's take a look at some of the conventions, because the sign conventions are important here, and you're already familiar with this one, but let's just recap quickly. Right now we know stresses we typically deal as positive, so these sigma x that you have and sigma y that you have over here, these are all positive stresses because it is tending to pull the element along both sides, right? Now tau xy, remember before going into this one, what we had decided about tau xy is that if the tau xy generates in a positive plane and points towards a positive direction, is positive. If the tau xy is generated in a negative plane, it points towards the negative direction, it is still positive. The only instance where tau is negative is that if it generates in a positive plane and orients in the negative direction, and so on. Just a quick example here. For example, if we take a look at this tau, it generates on a positive plane. Why? Because the outward normal is towards the positive x-axis and the tau itself points towards the positive y direction, so it is positive over here. Now let's look at this one. This one is this particular face is the normal to that is points towards the negative, while the tau also points towards the negative, so double negative is a positive. So in essence, all the stresses that you see, all the shear stresses that you see in this particular element are positive. So we are starting off with a completely positive element where the stresses are tending to pull and the taus are also positive. Now what we are going to study, if you take this element over here and if you rotate it about a particular axis, right, if the element becomes something like this, that is, you are rotating the element over, you know, a particular angle theta over there, and theta is also considered positive when it is acting in the anti-clockwise manner. So theta, the original x was here, I have given an anti-clockwise rotation of theta, which as per convention we are going to follow is the positive. Now about this theta, and remember this is within the same point within the body, within the same point within the body, you are, say you have a particular point, you're looking at planes like this, you're looking at planes like this, looking at planes like this, right? So within the same point in the body, if you give a rotation of theta, what happens to the sigma x and what happens to the tau xy, as you can see over here. After rotating this one, say the perpendicular axis becomes x prime. Now about x prime, how does sigma x change, and what is the changed value that is represented by the sigma x prime? What is the value of the sigma y prime? How does the shear change? What is tau x prime y prime? So this is what we are trying to find out over here. Now writing these expressions, that what is the dependence on these stresses on the original set of stresses that you have. So these are ones you can easily calculate from the fundamental relations which we have studied. Now about this rotated axis, to find this relationships over here, as you can tell, it involves a fairly, you know, exhaustive set of algebraic manipulations. So we are not going to write out every single step. It is very easy to do. I am here only going to guide you that how you know, take sections and then you balance, essentially balancing the forces and then back calculating the stresses and finding the stresses which are there, right? Now for this one, for this element over here, it is, you can think of it as simple as that if this rotation is theta over here, you can imagine this as within this element, if you take a plane theta, because you're looking at the same point within the element, right? So if you're taking up, you know, anti-clockwise theta over here, and if you take this small chunk, this small rectangle that you see over here, and if you resolve the forces about this x prime, you will end up getting that sigma x prime. So within the same place within the body, I'm just taking different planes. So if I take this original element and if I cut an angle of theta and I try to resolve the forces there, I will essentially get my, you know, my transformed set of stresses in the rotated plane. So if you take a look, and you know, you can take a look at these expressions in at your own leisure time, that if you take this small triangular element which I just isolated, and if I balance the forces over here, what you will essentially get, now we are slowly going into the transform relations, and this is where I want you to pay your full attention. We are slowly, you know, getting into how to get the sigma x prime, how to get the sigma y prime, how to get the tau x prime y prime that we have over here. Now if you resolve, if you write out all the stresses, and remember we always do force balance, we never do stress balance, because eventually your forces has to balance out. So if you do the, you know, the force balancing equation, and if you're interested, you can go through these equations, or you can take a look at any of the standard textbooks which are recommended for this course. You will see that the transformed sigma x prime, right, about this rotated axis that we have over here. So let me go back to the previous slide. This transformed sigma x prime depends upon all these set of stresses that you have over here through this particular relationship, and this is easy to remember. If you write it out a couple of times, it's very easy to remember. It is essentially your sigma x prime is sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cosine of 2 theta, where remember theta is that anti-clockwise angle through which you have rotated the element, plus tau xy sine of 2 theta. Right? So if you write it out a couple of times, it will make sense and it will have it ingrained in your brain, because you will see, so this is the sigma x prime. When you will see the expressions for the sigma y prime, remember sigma y prime is this guy over here, about acting about the rotated, you know, y axis, y prime axis rotated by the theta, and also the tau x prime y prime, which is this guy over here, which is, you know, this essentially this one over here. So let's look at all these expressions that you will see. right? So this is the tau x prime y prime that you will get. So this is the expression for that one, that is negative of sigma x minus sigma, and these are easy to remember. Trust me, if you write it out a couple of times, once you see the entire set of equations, let me maybe go to that will become easy for you, right? So now we have the sigma x prime, which we calculated like this. See, this is the sigma y prime. Now what is the easy way to calculate sigma y prime? You can again take an element which is rotated at a particular angle, and you can resolve the forces. Otherwise, the easy thing to do is that if you have the sigma x prime over here, remember, in this rotated element, if this face rotates by a theta over here, this particular face, the angle that it makes, so this face over here makes this face over here makes an angle theta with this horizontal axis, and this face, which was initially perpendicular at 90 degree, now it makes a theta plus 90. So in this expression, if you replace this theta over here with theta plus 90, you will essentially get this sigma y prime that you have. This stress you will get directly. So these are the expressions that you get. Now you see that how nicely symmetric these expressions are, right? So let's go ahead into the next slide to see all the expressions together so that it makes sense. Okay, so this is what we get over here. So we will come to this one later. So this is what you have overall. So if you have an element which is originally oriented like this over here, and if you rotate this element anti-clockwise positive with an angle theta about this rotated element, what are the stresses? Sigma x prime, sigma y prime, and tau x prime y prime. This is our objective. Now these are the set of equations that now you see how symmetric, nice, and beautiful these expressions are. You get sigma x prime as average of the stress, sigma x plus, this is the original stress in the original element, sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cosine of 2 theta plus tau xy sine 2 theta. Now to get the sigma y prime, I simply had to replace theta with 90 plus theta, and this gives rise to a equation very similar to this, and the only difference between them is that the sign flips for these last two terms over here. So the first term remains the same, the modulus of the terms remains the same, so only the sign flips for the last two terms. You have a negative over here, simply because you are replacing this theta by theta plus 90 over here. And the last expression is for the tau x prime y prime. This is also easy to remember. You see, in this expression compared to the previous ones, you do not have this first term that you see, you have the last two terms over here, and the only difference is that the first one is negative, and the cosine becomes sine, and the sine becomes cosine, and this one becomes a positive. So if you write it a couple of times, I encourage you to grab a notebook, write it a couple of times. It will get ingrained in your mind that you have over here. Now, one very important thing to observe, which will help you in deriving stresses on an inclined plane, is this interesting observation that I have noted over here. You see that in the original element over here, right, you have this sigma x and sigma y. So sum of these, sigma x plus sigma y over here. Now about this rotated element, you have the sigma x prime about this, sigma y prime about this, which are these expressions over here. If you add these two numbers, if you add this equation, if I call this equation 1 and if I call this equation 2, right, so if you kind of add these two guys over here, you will get this one. Now you see, once you add this, you get sigma x prime plus sigma y prime is equals to sigma x plus sigma y. So the sum of the normal stresses, this is very important, the sum of the normal stresses about any inclined plane remains the same as the sum of the normal stresses in the original plane, and it is valid for any rotation theta. If you have a rotated element or a straight element with a sigma x, sigma y, and if you take the summation of that, if you rotate that element about any plane, right, you will still see that some of the normals always remain the same. So this is an interesting and important observation over here. So these are the key takeaways. These are the overall, in the nutshell, what we discussed in this particular lecture, that if you have an element over here and if you rotate that one, these are the expressions for the stresses about the rotated element. Remember, it is at the same point within the structure. You're just looking at a different plane which is rotated by an angle of theta from the horizontal, with theta being positive anti-clockwise in this case, right? These are the set of stresses for the rotated element. So these are the three main expressions. Always remember, in the 2D element you have essentially three stresses to worry about. One is the sigma x, second one is the sigma y, and the last one is the tau xy, right? So these are the, for the rotated element, the stress, the set of stresses that you have over here. And also remember that the sum of the normals in the rotated element about any angle of rotation remains the same and is equals to the sum of the normal stresses for the original element that you have over there. Now that we have this very basic set of equations, let's go ahead and look at an example problem where we will be given an element and you are asked to rotate that element about a particular angle and find the set of stresses for the rotated element. So what you see in this problem example on your screen is an aeroplane structure. So which is the aeroplane, and for this aeroplane in a particular point within the aeroplane, you are given the set of stresses. Now this can be a result of many things. This may be the aerodynamic forces acting on the body, the weight of the passengers, the weight of the aircraft itself, and many different things. So for all these different things within this element over here, where these faces of this element are taken perpendicular to the longitudinal axis, you have calculated the set of stresses. Now the interest within for the problem is that if you take this element and within the same plane, say if you take a rotated element or in a rotated plane, if you are looking at it, how do the state of stresses and everything change? So this is what the problem asks you, that if for this element this is the state of stress that you have over here, now if you at the same location, if you take an element which is rotated at a 30-degree clockwise angle, remind the word clockwise, essentially at the same location, if you're taking an element which is rotated at a 30-degree angle, what is the state of stress which happens to that element over there, right? So let's go ahead and first draw this regular state of stresses. Let's mark our sigma x, sigma y, and the tau xy. Remember, those are always indicated, usually indicated for the element which is planes are perpendicular and parallel to the longitudinal axis. Then we are going to rotate the element to a 30-degree angle, and we will find what is the sigma x prime, sigma y prime, and the tau xy prime, right? So let me first quickly draw the original element and the rotated element and mark the stresses before coming back and calculating these different stresses which are there. So this is my original element which I have over here, which is essentially this guy over here. So as you see that in this particular case, what we had as per our convention is that sigma x was positive, and of the element we looked at, sigma x was positive when it is tensile, and the tau xy was positive when it was generating in the positive plane and oriented towards the positive, or generated in the negative plane and orienting towards the negative. For all other cases, tau xy is negative. Now let's take a look here that what are the different things which we are given. So here you see your sigma x is compressive over here, which is equals to this 80 MPa that you have. So sigma x comes out as negative, right? So let's write that down. What about sigma y? Sigma y is a positive 50. You see it's a tensile force, so sigma y is a positive 50. And lastly comes our tau xy. So you see, with my positive x and the positive y direction, tau xy generates in the positive on the plane which is for which the outward normal is the positive x, but the tau itself points towards the negative y direction. So the tau xy is going to be negative. So these are the set of stresses for our original element. Now it says for an element which is rotated at an angle of 30-degree, how do the set of stresses change? So let's go ahead and first draw the element which is rotated by a clockwise 30. Remember, clockwise means a negative 30-degree, because as per our convention we had taken the anti-clockwise theta as a positive theta. So let's go ahead and first draw a rotated element. So this is our rotated element that we have, which is inclined at this particular angle. Theta is a negative 30 degree because it's a clockwise rotation that you are having. See, this is similar to this one. If you see this element over here, you know, this is also that 30 degree angle. So it is a clockwise rotation. So for this element, I am going to find the set of stresses which are there. I cannot directly mark it here because first I have to see whether it is a positive or a negative or not. So let's write down the basic equations that we have, then come back and substitute the numbers, and let's see what we get. So let me go ahead and write the equations. So I have written out the overall expressions, overall equations over here. Now what all I have to do is simply I'm giving these values sigma x, sigma y and tau xy. All I have to do is plug these things over here, punch in the calculator. Remember, you have to here in all of these cases that theta that you have over here, this particular theta is always going to be minus 30 degrees that you have over here. So let's make a quick note of that. So this theta that we get, so if you plug in all the values, what you will get, I have all this worked out here, you will get a value of sigma x prime which comes out as minus 25.8. Your sigma y prime comes out as minus 4.15. And lastly, your tau x prime y prime comes out as minus 68.8. Now that we have about this rotated axis, now that we have these different stress values which are there, so now we are going to go ahead and mark these in our rotated element that is there. So let's go ahead and mark that. Always you have to be careful about the direction. See, in this one, sigma x prime comes out as a negative 25.8, so that means it must be compressive. So this is my x prime, and you will have a force, a compressive force like this acting in this direction and in opposite compressive direction because it has to balance out. So let's just, you know, mark those guys over here. Now your sigma y prime, you see, although in the original element your sigma y was a positive tensile, here it becomes a negative 4.15, so that is also compressive. And lastly, the tau xy, that also in the original it was negative, it is going to be negative, and also remember the direction, it is going to be negative, so it originates in the positive phase but points downwards over here. And as I said earlier, that if you draw one of the taus, all the other taus get automatically, the directions get automatically fixed by that. So I hope this particular problem example was clear, that we had an element which is, you know, originally at this plane, originally the faces are oriented about the perpendicular and the parallel, right? And then we gave a rotation of 30 degree, and for the at the same location, if you look at a plane which is rotated at a clockwise 30 degree, these are the different set of stresses that you get within that particular element that is there. Now remember, these arrows, these pointy arrows, these are equal and opposite over here. So if this is 25.8, this guy is also 25.8 over here, and this was 4.15 here. Also you will have this as 4.15. Okay, so I hope this problem example made sense to you. Let's go ahead and look at our next topic. In the last lecture and the problem example we saw, what we observe that when you take an element and if you rotate it about particular angle, your stresses change. Your sigma x, sigma y, tau xy becomes sigma x prime, sigma y prime, and the tau x prime y prime. What we are going to see now is that does there exist some particular angles of rotation for which your normal stresses become their respective maximum and minimum, and those angles of rotation and the planes about which they rotate, they are known as the principal planes. As you can see already written here, there's a principal planes, the principal directions. And does there exist another angle of rotation for which the shear becomes maximum? So let's go ahead and take a look at that. Now, as you have already seen, this is what we saw, that if we take an element like this over here and if you give a rotation, again we are dealing with the positive rotations here, theta over here, general positive. So for which you have these rotated about the rotated plane, you have this updated state of stresses that is there. So what we are trying to address is that does there exist an angle of rotation theta, that is, let's call that theta equals to theta p, at which the stresses sigma x prime and the sigma y prime reach their respective maximum and the minimum values respectively. Now this is important. Why does it happen that when one of them reach their maximum, the other one reaches the minimum value? Because remember that we have that relationship always value. So let's just quickly write that. We have the relationship that sigma x prime plus sigma y prime equals to sigma x plus sigma y. So that means that if one of them is reaching their maximum value, the other one must reach the minimum value to always keep the addition as a constant number that you initially started with, right? So this is important. So that is why when one of them reaches their maximum, the other one must reach the minimum value over here, right? So now the question is that how do we find this theta p, that rotation where one of them becomes the maximum and automatically the other one becomes the minimum over here? Well, the answer is very simple, and I know you are thinking about this already. For example, if I take this expression and if I differentiate this expression with respect to theta, I will get that particular angle at which my sigma x becomes a maximum and sigma y becomes a minimum, right? So we have to essentially do the differentiation. So if you take this expression and then you differentiate, so this step shows the differentiation that you have over here. These are very simple algebraic manipulations, so I'm avoiding writing it and doing every step. If you're interested, you take this expression, you differentiate it, you will get this one over here. Then if you equate this expression to 0, that will give you the theta, that will help you calculate the theta at which the maximum happens. And it turns out to be the expression for theta boils down to something like this. So tan 2 theta p, and theta becomes equals to theta p because p, remember, p represents the principal direction. So let's maybe make a note of that. P means the principal direction, right? So in this principal direction, your sigma x is going to be maximum and automatically your sigma y becomes the minimum, or vice versa, depending upon the sign and everything, right? So this expression comes out to be a simple expression, something like so. This is the ratio of the shear in the original element tau xy divided by sigma x minus sigma y divided by 2. Now what does this mean? So this means that now since it is tangent of 2 theta p, that means there are two angles 2 theta p separated by 180 degrees, and the subscript p, as we wrote over here, it represents the principal direction. So about one of the theta p's you have the maximum stress, and about the other theta p you have the minimum stress sigma 2 that is occurring over here. So now you're replacing sigma x prime with the maximum stress sigma 1, sigma y prime with the minimum stress sigma 2 over here, which is separated by this that 2 theta, that is 180 degrees over here. Now since in this one you have this 2 theta p separated by 180 degrees, theta p, that is 2 theta p divided by 2, theta p must be separated by 90 degrees over here. So that is what is over here. So the actual angle of rotation theta p therefore rotates by 90 degrees. So let's take a look how that element looks like. So this is again the general description for that one. So what we have done is that similar to what we did before when we were just giving our arbitrary angular rotation theta, now I have rotated about a particular angle of theta p1 about the x-axis over here. Now since this is theta p1, the original faces were perpendicular to each other. This one rotates by an angle of theta p2, which is nothing but theta p1 plus 90 degrees. So this is what it is. So this is the angles are separated by this rotates by this 90 degree over here, because two theta p's are separated by 180 degrees. So if one of them you're rotating by theta, so it's easy to keep a track of. If you know the rotation of one, so the other one must be the theta p2 must be equals to 90 degree plus theta p1 that you have over here, right? And also remember that these are the stresses. So sigma 1 is the maximum stress and this is the minimum. So now if you go back and if you substitute this tan 2 theta p2 in the general expressions, remember the general expressions for sigma x prime and sigma y prime, which we wrote out in the previous lecture. If you substitute in those general expressions, now remember for the principal direction, sigma x prime becomes equals to sigma 1, sigma y prime becomes equals to sigma 2, and this is the general expression that you have over here. So for sigma 1 you are going to use this positive sign, so the expression boils down to sigma x plus sigma y by 2. This is the first term of that transformation equations, remember, so that remains the same. And for the remaining term, it is essentially the square root of the sum of squares of the last two terms, that is sigma x minus sigma y2 square plus tau xy square. Now for sigma 1 you are going to use the positive sign because that is the maximum stress that you want to get. For sigma 2, which is the minimum stress, you are going to use the negative sign. And you see that your relationship is preserved. So at about any angle of rotation, if you want to write it, even here also you have sigma 1 plus sigma 2 is equals to, for any angle of rotation, sigma x prime plus sigma y prime, which is again equals to your sigma x plus sigma y. So that also always stays value. So if you add sigma 1 plus sigma 2, this term cancels out, so you end up with sigma x plus sigma y. Okay, and also this is the angle of rotation which we wrote in the previous page as well. So that is tau xy divided by sigma x minus sigma y divided by 2. So what it is, so these expressions give you the maximum and the minimum principal stresses, and since as I mentioned these are the places where the maximum happens over there, so these are the places where these are known as the principal planes. So these are the principal planes, essentially means the planes where you cut your element or where you cut within the structure where your stresses essentially peak up, your normal stresses reach up their maximum and the minimum values over there. Now let me point to you something that is very interesting. If you take a look, right, if you take down, I want you to spot the difference over here. So this is the original element which we started with. We have not rotated it or anything. This is the original element we started with. Now for this element, when I gave a general angle of rotation theta, any angles, anti-clockwise angle theta which we are giving, this was a set of stresses about that rotated plane where we have the sigma x prime, sigma y prime, tau x prime, y prime about this angle of rotation theta. Now when I am rotating about theta equals to theta p, that is about the principal planes, you see this is the set of stresses that we have, that is sigma 1 this is the maximum stress that you have, sigma 2 is the minimum, or vice versa, depends upon the sign and so on. So this is when it is rotated at theta equals to theta p. Now what I want you to observe is the difference between this and this over here. Do we have the normal stresses? Yes, we do have the normal stresses, but what happens to the shear? So the shear essentially vanishes, and if you go back and the tan to theta p that we calculated, if you go back and plug that in the tau xy equation, what you will observe is that when an element is rotated about the principal direction, your shear stresses essentially vanish. So this is a very important observation that you must keep in mind, that if you take an element and if you rotate it about the principal planes, your only normal stresses remain, and those normal stresses are the maxima and the minima, and the shear stresses vanish. So this is important, please remember this one. So tau x prime y prime about the principal planes, it vanishes, that is tau x prime y prime at theta p1 at theta p2, both about this face and this face is vanished. And it's easy to note, if the remember from complementarity, if your tau vanishes in one of the places, for all the across the 4 places it has to go. If it occurs in any one of the faces, it has to crop up in all the faces that you have over there, right? So in summary, 3 important things to remember. First of all, that about this theta p1, theta p2, you have the principal stresses. The stresses are known as the principal stresses. Why? Because your element is rotated about the principal directions. Also, this, how do we get this angle over here? We simply substitute this in this expression. You will get theta p1 90 degree plus theta p1 equals to theta p2. So this gives you a principal planes, and lastly your tau x prime y prime was 0 on the principal planes over here. Now with this, what did we get? We got that if you take an element and if you rotate about a particular angle theta p1, theta p2, you only have the principal stresses and no shear stresses. Now remember, the original element which we started with was something like this over here. And what we did to essentially get this one is that we just simply differentiated this particular expression. So this is the slide we saw a few slides back. We just differentiated and we got theta p. Now, is there, the second question that we have, that we're trying to address in this lecture, is that is there another angle of rotation where your tau xy about a particular rotated angle, is there any angle where your tau x prime y prime becomes the maximum values? We know that when rotated about the principal direction, tau x prime y prime vanishes. So is there any other angular rotation where the shear becomes a maximum value? The answer is yes. And how do we get that? How do we get that particular point? So the question again is that, is there an angular rotation theta s? Now I'm going to call this theta s. Remember theta p, where we were having the normal stresses reach their principal values or becoming principal stresses. Theta s is the angle where your tau x prime y prime reaches the maximum value. So how do I get that? The answer is simple again. I take this expression and I differentiate with respect to theta. I equate that to 0. So I get a value of theta s at which my shear stresses become maximum. Now, do you think that the plane where the shear stresses become maximum, the normal stresses disappear? Because in the principal plane we saw that where the normal stresses were becoming maximum, the taus were vanishing. So does it happen in the contrary way as well, that where your tau x prime y prime becomes maximum, does sigma 1 or sigma 2 or the sigma x prime and the sigma y prime vanish? Let's take a look. So it so happens that if you take this expression and you differentiate with respect to this one, you get something like this over. So this is the tan 2 theta s. The tan 2 theta s so this becomes 2 theta, since this is tangent, 2 theta s separated at 180 degree, where your shear stresses become the maximum over there, right? Now remember, shear is an element which is like if you have it on one particular face, all the other faces have equal values, modulus values, and the directions are automatically fixed by one of them. Now if you take this expression over here, now let's take a look at this expression. You see that previously for the principal directions we got this expression, and you compare this value with this one over here. What do we see here? What was the tau xy? It has gone below, and what was the denominator becomes the numerator over here, and this whole thing has a negative sign. So this expression is simply a negative reciprocal of this expression over here. And what does that mean? Remember your trigonometry. So it means, since it's a negative reciprocal, that means your theta s and theta p is separated by an angle of 45 degrees. It is such an interesting observation that you see over here. That essentially means that your plane of maximum shear is 45 degrees away from your principal plane. Again, let's take a few steps back. We had an original element. We took that element and rotated about a particular theta p, where we got the principal stresses. From that, if you deviate a further 45 degree, you will get the plane where you will have the maximum shear stress that is occurring. Now coming back to our original question, does the sigmas vanish? The answer is no. So although for this theta s rotation that you have over here, and here this rotation is shown about the clockwise direction, when we look at a problem, this will make much more sense to you, that you will see that at these rotations, at this theta s rotation, your tau x prime y prime becomes with the maximum tau max. So this is, if I just write it out, so this is essentially tau x prime y prime maximum, which is this guy over here, it becomes this expression. Remember, we have seen this expression previously in the principal stresses, that last element, that plus minus square root of sigma x minus sigma y by 2 square plus tau x y square. That's the only thing that remains when you calculate your maximum stresses. And it so happens that in these planes where we have this maximum stresses, your normal stresses do not vanish. Your normal stresses becomes equals to this average stress over here. You may average means sigma x plus sigma y by 2, which is the original stress in the original element, right? So at the planes of the maximum shear, the normal stresses still exist. Now you may remember these expressions from where, remember the chapter on torsion that we studied, where you had a pure shear element, we rotated about, we were giving twisting to the chalk and it was breaking, and at that 45-degree, remember, you had the tau as tau max and your sigmas was the sigma average, right? So this is essentially what you get over here. So in a nutshell, again, when you take the element and if you rotate it about that angle which gives you your maximum shear, at that position you will still have the normal stresses, and the value of the normal stresses across all the four faces, the directions will depend upon the directions of the stresses in the original element. So don't be bogged down by the directions. When we calculate that, you will see how they change, but the magnitude is going to be the average of the original stresses that you have, right? So to summarize this entire lecture, what we have over here is that your principal stresses represent the point of the maximum and the minimum stresses, that is sigma 1, sigma 2. When you have in the principal stresses, there will be no shear stresses, that is tau x prime y prime becomes equals to 0, right? Now when you have the element rotated at the angle where it gives you the maximum in plane shear stress, in that case your sigmas or the normal stresses do not vanish, but it becomes an average normal stress which also acts on the element. And lastly, that the plane for the maximum shear stress is oriented at 45 degrees away from the element which represents the principal stresses over here. So lots of different formulas, but hopefully easy to remember. Let's go ahead and solve a problem to see that for an element how we can get the planes for the maximum principal stresses, or the principal stresses as the maximum and the minimum, and the maximum in plane shear.